Are you still here? Right, that's good. Okay, now we move on to the next topic, which is this is still under chapter 1. Okay, we're talking about the pH of the solution. And pH, so we know that the pH, so this is the pH scale, and 0 to 14. 0 to 14, so the acidity is start from 0 to 6. 7 is neutral, and alkaline is 8 to 14. Okay, so these are the keyword that you're going to understand. Okay, when you learn about the pH, and there is a H plus or H minus or hydroxyl, not hydroxyl, hydroxide. Okay. pH, acid, base, or sometimes we call it as alkali, neutral, phase scale, also buffer. Okay, for water molecules, it can be self-ionized in water, self-ionized. Okay, these two molecules of H2O will form H3O plus OH minus. And this actually double arrow showing that there is a reversible action, which means that this H3O plus and OH minus can become H2O again. So this is what we call it as reversible action. It's a reach a state of dynamic equilibrium when water molecules dissociate at the same rate. Okay, so that's why inside the water too, there is also H2O, there is also OH minus and also H3O plus. Okay, for this H3O plus, a hydrogen atom participating in a H bonding between two water molecules shift from one molecule to the other. The H atom leaves its electron behind, producing H plus. Okay, H plus meaning that this electron ni, and H plus lah, H3O minus, the H plus tu, meaning that they will give a electron. So that's why in here in the what do you call the orbital here, there is no electron. It just left only proton. So that's why H plus ni we also call it as a proton. And H plus and also proton because it's only proton. The combination of hydrogen ion and a water molecule to form H3O plus. Water plus proton. Proton ni comes from the hydrogen lah. Okay, and we call it as a hydronium. Hydronium because it have a excess what do you call it, positive charge. Not lack of electron, so that's why it will give a positively charged hydronium ion. But sometimes we just put it as H plus only. H plus and H3O plus is all the same. And sometimes we call it as H plus, sometimes we call it as a hydronium ion here. Okay. H plus and OH minus are very reactive. Okay. Each change in the concentration can drastically affect a cell's protein and other complex molecules. So that's why pH is very important. Because pH with a solution with a different pH, it will have a different H plus and also different OH minus. And if there is a difference in terms of the concentration of H plus, it will affect the cell proteins and also the other complex molecules. Okay, the water molecule that lost a proton here is now a hydroxide ions. The charge is 1 plus. So we call it as hydroxide ion or hydroxide, not hydroxyl. Hydroxyl with SYL, hydroxyl, and you can see it in the alcohol, OH, COH. OH2 is a hydroxyl, not hydroxide ions. Okay, so OH minus is a hydroxide ion, and the charge is 1 negative. Okay, we know that when we talk about the pH ni, and we're talking about acid and also base or alkali. So the acid ni, these are some of the example of the acid, and battery, lemon, and lemons, apples, and lemons are highly acidic than the apples. And neutral milk, for example, or water. And basic or alkaline, household cleaner. Okay. So acid is a taste sour, react with some metals to give off hydrogen gas and conduct electricity in solution. And base taste bitter, feel slippery, and like for example soap. Okay. Sabun, dissolve fats and oil. So what is acid and base? Acid ni dissolve in water and it will donate additional H plus to the solution. So inside the solution, acidic solution, there will be a lot of H plus as compared to the OH minus. So once we put the hydrochloric acid, for example, hydrochloric acid or H2SO4, sulfuric acid. So those contain a lot of H plus. So once we put it in the solution, so it will have a lot of H plus. Once there is a lot of H plus, the hydrogen concentration will be increased. This is the symbol of the concentration. And bracket ni is a concentration of hydrogen plus. The concentration is really high in the acidic solution. And the acid is also called it as a proton donor. Okay. Example of the hydrochloric acid is the HCl, where in water it will dissolve and it will dissociate to hydrogen plus or proton H plus chloride ion Cl minus. So hydrogen's ion dissociate from chloride ions, okay, H plus and also chloride ions. Same like sodium chloride, Na plus and also Cl minus. So this is full charge, and unlike water is a partial charge or slightly charged. So this is full charge lah. Okay, base or alkali, base dissolved in water, take up additional H plus from the solution, dissociating to form hydroxide ions and combine with H plus and forming a water. Okay, so inside the basic solution there will be a lot of OH minus. So the concentration of H plus will be decreased or will be lower. It is also considered as a proton acceptor. The example of the base is ammonia. Ammonia acting as a base when the unshared electron pair in n valence here, okay, shell attracts a H plus and from the solution, and it will form a ammonium ions, and H plus 2 is ammonium ions lah. Okay, but the ammonium ion since is considered as weak base. Another example is sodium hydroxide, NaOH. So inside the water, there is just only Na plus. Okay, it will form sodium plus, sodium with a positively charged, and OH minus. Okay, and if you see the symbol here, so this is the reversible reaction, but this one is a straight. Okay, it's not reversible. It will produce sodium plus and also hydroxide ion. Okay, one more thing in neutral. So what is a neutral? Neutral is a solution in which the H plus and also OH minus concentration are equal. Okay, so remember that in this solution, in the acidic solution, there will be a lot of H plus. Okay, or proton. There will be a lot of proton. You can see the example is hydrochloric acid. Hydrochloric acid in water, it will form H plus and also chloride ion. So there will be a lot of H plus lah. For base, it's different from the H plus. Okay, in the basic solution or alkaline solution, there will be a lot of OH minus. And we see the example of sodium hydroxide. Sodium hydroxide in water, it will form sodium plus and also OH minus. So there will be a lot of OH minus. So because of that, and because there is a lot of OH minus, and this OH minus can interact with H plus, forming a water. So the number of H plus will be decreased, will be lower. The number of H plus though, or the number of proton will be lower. Okay. And neutral ni there is a balance and between the H plus and also OH minus to neutral. So these are the example. Okay, I want to show that at lower pH tu, okay, 0 to 6 tu, the concentration of H plus is much higher than the OH minus. And neutral, the concentration of H plus and OH minus tu almost the same. Okay, like the pure water, seawater, and at higher pH number, 14 or 13 tu, OH minus tu is more than the H plus. Okay, so if you see this scale, okay, you can see that the lower the pH value to at 0 to 1, for example, hydrochloric acid. Hydrochloric acid ini is very acidic. You see the picture there, it's corrosive. And not corrosive, the irritant. And it can, it's very dangerous lah. Maybe corrosive to metal, causes severe skin burns and eye damage, may cause respiratory irritation. So it's very, very dangerous to us because it's very reactive. Okay, we cannot consume this hydrochloric acid. However, we can consume weak acid, vinegar, for example, cola, and tomato juice. So these are the weak acid. And also, of course lah, we can drink pure water. Sodium hydroxide and sodium hydroxide pellet. See the picture there. So this is the picture of hazardous. It's a hazard to human. It's also corrosive to the metals, corrosive to our hand or to our skin. So we cannot drink this, or we cannot have interaction with the sodium hydroxide. However, milk of magnesia, okay, so we can consume this at weak base. So there is actually strong and weak acid. Strong acid or strong base cannot be eaten. It's very hazardous to human. However, for the weak acid, also weak base, it can have an interaction with human. Okay, for the strong acid, for example, HCl, it will dissolve in water forming H plus and also Cl minus. Sodium hydroxide, it will dissolve forming sodium Na plus or and hydroxide ion. So the single arrow in the reaction meaning that the compound dissociate completely when mixed with water. So Na plus and hydroxide ion will not combine together, will become sodium hydroxide. No. Okay, unless there is a energy to combine it together. However, for the weak base or weak acid and double arrow interaction, the binding and release of H plus are reversible reaction. Okay, reversible. So there is actually in water too, it will form carbonic acid and so bicarbonate ion and so hydrogen ion. It's a reversible release and accept back H plus. So that's different between strong and weak acid. And for the strong acid, there is a dangerous to human, or strong base is dangerous to human. But for the weak acid and weak base, they can have interaction with our body. Okay. So what are the example of strong acid or strong base or example of weak base? And you can see from here lah. So these are the example of the weak acid, vinegar, cola, tomato juice, lemon juice. Okay, so those are weak acid. Gastric juice ni in our stomach, and gastric juice ni or stomach fluid, it's very acidic. It's 1.3. Okay, why? Because the purpose of gastric juice too is to decompose food that we eat. Right? Unlike saliva and ileo kita ni, mulut, our mouth. So the pH is around 6 to 7. Okay. So once the food go to esophagus and goes to the what they call this, the our stomach. So the stomach to uh, the uh, very acidic solution to will decompose the food. And okay, these are the example lah. Kan, battery is a 0, the pH, and the drain cleaner is 14, and bleach Clorox, for example, Clorox 2 is 13, ammonia solution 11, and so on. Stomach tablet is 10. Why? Because you want to increase it. If you got a gastric problem, then it can increase the pH, increase the pH, so that will no longer have a gastric condition lah. Okay. Okay, a little bit about the pH scale. Okay, in any aqueous solution at 25 degrees Celsius, the product of H plus and OH minus to, and the concentration is constant, which is around 10 to the negative to the power of negative 14. So that's why it's in neutral solution, and there is an equal of concentration of H plus and also OH minus, which is 10 to the power of negative 7. And the pH of the solution is defined as the negative logarithm. It's a pH equal to negative log concentration of H plus. So that's why for a neutral aqueous solution, and it is a negative log 10 to the power of negative 7, it equal to pH 7 lah. So pH 7 because it has an equal number of H plus and also OH minus. pH decline as H plus increase and at the acidic solution lah. So a solution of pH 10 has H plus of 10 to the power of negative 14 and OH minus of 10 to the power of negative 4 molar. It's molar lah. So each pH unit represent a tenfold difference of H plus and OH minus. So that's why, and I want to say here is that because it is log, because of the log too. It's not just simply pH 1 is greater than pH 2. pH 2 is greater than pH 3. No, actually it's a what do you call this? The difference is very significant. A solution of pH 3 is not twice as acidic as solution of pH 6, but 1,000 more acidic. And when the pH of a solution changes slightly, the actual concentration of hydrogen plus and concentration of a hydroxide ion in the solution change substantially. Okay, so that's why it's very significant. Okay, in one pH and another pH. Okay, so there is one topic in the pH which is very useful when you come up with experiment. We call it as buffer. So what is a buffer? A buffer solution resists a change in pH when small amounts of acid or base are added. Okay, and if you see here, this is the water having a pH of 7.0. Once we put acid, for example, like hydrochloric acid H+, so the pH will significantly drop. At pH 3.2, it will become acidic. However, if we put water and plus buffer, okay, if we put some amount of acid, for example, hydrochloric acid, so the pH will still stable. It just only change to the lower pH 6.8. Similar to this one. Okay, after we add base alkaline, for example, like sodium hydroxide in water, so it will turn to the basic solution, alkaline solution. The pH is around 12. However, if you put a buffer, okay, so the pH is 7.0. Okay, and it does not change much lah, and just only 7.2 only. So the buffer ni, it can actually minimize the change in the concentration of H plus and also OH minus. and accepting H plus from the solution when they are in excess, and donating H plus to the solution when they have been depleted. Okay, what is composition of buffer? So its acidic buffer is made by mixing a weak acid with a solution of salts of a strong base. So this is example of the buffer solution, carbonic acid. So it's a weak acid. So if we put so carbonic acid is one example of the buffer solution lah. Okay, it's a weak acid. So if we put this H plus hydrochloric acid inside the carbonic acid solution, carbonic acid solution, so the pH will not change differently, okay, significantly. So what's the importance of buffer system? Okay, it will maintain homeostasis in our body. It can regulate enzymatic function. It can control pH in biochemical reaction. Okay, so it's involved. This buffer actually is very important in our body. Okay, if we does not have this buffer system, so in our body will what do you call this, react with the what do you call it, the acid lah, and also base. Okay, so we go to the section break. So hopefully that you understand what is a pH. Okay, you learn about the pH. There is a starting from here, self-ionization of water. Okay, the pH scale from 0 to 14. There is a acidic, neutral, and also basic. So acid is a pH below 7. Base is a pH more than 7. And in the acid there is a lot of H plus, and the base there is a lot of OH minus. Okay, a higher amount of OH minus. And you can see there is a strong acid or strong base, weak acid, and also weak base. And these are the pH scale with the example of the compound, the pH scale, and buffer. Okay, the importance of the buffer. Examples of the buffer is a carbonic acid, and also the what do you call this, the acetic acid. Okay, and then some of the importance of buffer system. Okay, I looks at the clock now is 11:50, 55. I know you want to be ready with other class. Okay, do you have other class after this?
Yes.
Okay, right.
Yes, sir.
So I think you have a section active learning. Okay, just one slide only. I want to come up with the example of the importance of pH. Okay, so individually find information about this example of the importance of pH. Arrange the information in one slide and put it in the FB group. This is example lah. Okay, pH in our stomach, for example. Like I told you about the importance of the low pH in our stomach. So you can put it some points here using smart art. So put a picture here. Okay, and like same like active learning. Okay, put in the comment section in the FB group. Okay, so this is summary for this class, for the whole class for 2 hours, and you understand the chemistry of, hopefully you already understand the chemistry of water. You can discuss the uniqueness of water, and you can understand the fundamental of hydrophilicity and hydrophobicity, and understand the principle of pH. Okay, so I think with that, thank you very much. I will put this video in the Facebook group, and then make sure that you always open to the Facebook group to see the announcement, and do the activity, and the activity that you have done. Okay, I will put that as a bonus mark. So I think I will stop here.